Welcome again to one more webinar as part of the Innovation and Precision Eye Health webinar series. My name is Regan Ashby. I'm assistant professor at the National University of Singapore, visual neuroscientist by training. I'm also the head of visual neuroscience at the Singapore Eye Research Institute, and the founder of this webinar series. So tonight, it gives us great pleasure to welcome my colleague and friend, Dr. Regan Ashby, to give this webinar. So I'll start with an introduction of Dr. Ashby, who is Associate Professor of Neuroscience at the University of Canberra, Australia. So Regan is very well known in the field of myopia. He's known as one of the leaders in the field, actually. And he's focusing on molecular pathways to prevent myopia, but also underlying the development of myopia. One thing I need to mention about Regan's career, and I think this is one of the highlights, if I'm not mistaken, we always say that time outdoors is protective against myopia. So Regan was one of the first people to understand and discover why is time outdoors preventive and protective against myopia, and at least untangle one of the features of outdoors time that allow for myopia prevention and control in children. He's focused a lot on animal work, but through the understanding of the molecular pathways for myopia and myopia prevention and control, he's now developing novel pharmacological treatments for myopia that are entering phase 2 clinical trials. So Regan has obtained several prestigious awards, including the Attempto Prize for Neuroscience in Germany and the Carl Zeitz Young Investigators Award. And the title of his presentation tonight is "How Does Being Outdoors Prevent the Development of Myopia? And Can We Use This Knowledge to Develop Novel Clinical Treatments?" So Dr. Ashby, welcome to this webinar session. We look forward to your talk. And just to specify one more thing, at the end of this session, I will be joined by two of my colleagues from NUH, Dr. Janice Lam, who is a consultant in pediatric ophthalmology at NUH and assistant professor at NUS, and Dr. Katrina Gounadi, who is associate consultant in neuro and pediatric ophthalmology at NUH, and we'll have an exciting discussion on the topic with Dr. Ashby by the end of this webinar. So if you have any questions, please use the Q&A button at the bottom of the screen to ask your questions, and we'll make sure to ask them at the end and discuss them. So without further ado, Regan, thanks again for accepting our invitation, and we look forward to your talk.
Thank you, Raymond. Thank you for inviting me. Let me share my presentation with everyone. Everyone can see that, I hope.
Yes.
Excellent. All right. Well, thank you for inviting me to talk about the protective effects of being outdoors, the potential mechanisms involved in driving that protection, and what novel clinical interventions we could derive from this knowledge. Important before I start is to disclose, as I've noted here, that I'll be speaking about the use of levodopa near the end of this talk for the treatment of myopia. And I, or more specifically, the university I work for holds a patent on using levodopa for this means. Now, this has actually been a really timely talk for me because currently we're writing what's referred to as a white paper for the International Myopia Institute on time outdoors, light, and so forth, and its potential protective mechanisms. And so this really forced me to read up on some of the latest literature, and there really is a lot of literature coming out in the field of myopia. I'll only be summarizing some of it today. You could talk for 5, 6, 7 hours just on this topic alone. Just so that we're all on the same page, I'm just going to go through some basics first, and then we'll move into some of the information about time outdoors. So during normal ocular development, the axial length of our eye is matched to the refractive power of our cornea and lens, so that when we're viewing an object in the distance, that image can be focused clearly on that neural layer that sits at the back of the eye, the retina. What occurs in myopia is that we have this excessive elongation of the eye, and we now have a mismatch between the optical powers in that cornean lens and the axial length. And now our image, when viewing an object at a distance, is focused in front rather than on the retina. And this causes the image to appear blurred. Now, there's 3 points I want you to keep in mind as I go through this talk today. The first is that eye growth appears to be regulated locally by signals generated here in this neural layer, the retina. Now, although the retina takes those photons, translates them into electrical signals, sends it back to the brain where we perceive the visual world, the brain does not appear to be critically involved in the regulation of ocular growth. Rather, this occurs for the most part locally within the eye. So it's that retinal layer. The other thing I want you to keep in mind is that normal growth, like so many other parts in our body, shows rhythmicity. That is, it cycles between day and night. It has this diurnal pattern. So, for example, the axial length of the eye grows more during the day than during the night. And I'm going to talk about how this rhythmicity may be affected during the development of myopia and how reintroducing this rhythmicity may help us protect against it. Finally, keep in mind that any treatment goal is to inhibit this excessive elongation of the eye. And we're going to talk obviously about moving from myopia to hypomyopia. So the greater this axial length that occurs, or the greater this disparity between the length of the eye and the optics, the more you move towards potential pathological changes within the eye. And the cutoff that we're used in the field is always moving from myopia, which is measured in diopters between 0 and 6, moving into that hypomyopia, so greater than 6 diopters worth of myopia. Now, why has myopia become so interesting in the last couple of centuries, or decades, I should say? And that's mainly because the prevalence of myopia has increased dramatically in the past 50 years. And this is most notable, as you can see here in the world map, in urban areas of East Asia. And obviously, talking to a Singaporean audience, that is quite evident to you guys. That here in these urban areas, kids of school leaving age can be as high as 90% myopia rates by the time we're exiting. It is predicted that by 2050, 50% of the world's population might be myopic. And worryingly, roughly 10% of those individuals are predicted to have high myopia. And it's this group that we're worried about the potential pathological changes. So going on to that, myopia is now the leading cause of low vision worldwide. And the thing we have to remember is, though we can optically correct the refractive error, so that mismatch between the optical component at the front of the eye and the axial length, this is not addressing the potential pathological changes associated with an eye that's become enlarged. That enlarged eye puts you at an increased risk of degenerative retinal changes, cataracts, glaucoma, optic disc tilt, pits, etc. I'm showing some examples over here from beautiful work done by Flitcroft and colleagues, looking at 2 things, maculopathies and retinal detachments, and the odds ratio of developing these clinical pathologies. Down the x-axis is the amount of myopia. And so you can see here it would be roughly -6, where we go from myopia and drop over into what's referred to as high myopia, or sometimes referred to as pathological myopia. And you can see once you move into that area, the odds ratio of developing either a maculopathy or some type of retinal detachment are quite significant compared to back here with no refractive error. Therefore, one of the primary aims actually in the field, although we'd love to prevent the onset of myopia, one of the primary aims is to primarily stop the movement from myopia into this high myopia, and therefore the increased risk of these pathological changes. The other thing to note is that the diagnosis and treatment of myopia really does place a significant physical and financial burden on health systems. An example just here is that it was estimated it costs roughly $14 billion in the US in 2010 to treat, diagnose refractive error and low vision, which myopia makes up the largest category of. So what about this idea of time outdoors? Well, in the mid-1990s into the early 2000s, a number of epidemiological studies reported that the greater the outdoor activity a kid undertook, the less likely they were to develop myopia. A later study by Rose and colleagues actually indicated it was rather total time spent outdoors that was the protective factor, rather than doing a specific activity outdoors. Numerous studies have now shown this correlation between spending time outdoors and a reduced incidence of myopia onset, although I must acknowledge that not all studies have observed this. But from this, we generate this famous figure from Rose and colleagues, which looks at two components: near work, which is commonly thought of as a myopogenic stimuli, and time outdoors, which is thought to prevent the onset of myopia. And what you can see here is that if you spend large amounts or high levels of time outdoors, whether you spend low, moderate, high amounts of time doing this near work tasks, you have a reduced odds ratio of developing myopia, compared to if you spend low amounts of time outdoors, but high amounts, for example, of time doing near work tasks, your odds ratio of developing myopia are significantly higher. So from these initial studies came intervention trials to look at increasing the amount of time kids spend outdoors. And I'm just showing you two of the early studies that were undertaken in this space. There's been a number of studies since. The first one in China looked at 6 schools, 952 children in the treatment group versus 6 control schools, 951 in the control schools. The kids were 7 years of age when they started the trial, so grade 1 students. And what they did for the treatment group was increase the amount of time spent outdoors during the school week by 40 minutes per day. And the study ran for 3 years. Roughly at the same time in Taiwan was another study running similar structure, one treatment school with 333 kids versus one control school with 238 kids. This was aged 7 to 11 years of age. But instead of 40 minutes, this study increased it by 80 minutes per day during the school week, time outdoors, and they ran for 1 year. What you can see down here is the Chinese study with an increase of 40 extra minutes per day, saw a 23% reduction in the incidence of new cases of myopia. Whereas the Taiwanese study, which doubled that amount of time, so going from 40 to 80, saw roughly double the amount of protection against the incidence of new cases. Really showing that by using time outdoors, you could affect the onset of myopia. Now, what's been really interesting is while the relationship is solid between the idea of spending time outdoors and reducing the incidence of new cases or onset of myopia, it is much less clear when it comes to progression. If there is an effect on progression, it's quite weak compared to the effect we see on onset. I'm just showing here one meta-analysis that was undertaken in 2017 using the data at the time. What you can see here with the studies they were looking at with spending greater amount of time outdoors and progression, one study reported a significant effect on progression. One saw an effect, but it didn't reach statistical significance. But the vast majority of studies did not see an effect of spending greater amount of time outdoors on progression. The question is, what could explain this? This strong effect on onset, but a weak effect potentially on progression. One possibility, and something I'll speak in the slide following, is that after onset of myopia, the retina is less sensitive to the protective properties of time outdoors. And I'll explain in a moment what I mean by that. Second possibility is that greater exposure time is required to inhibit progression versus onset. Now, that could be because of a change in sensitivity in the retina, or it could be that more time outdoors is required to counteract whatever the myopogenic stimuli that is driving progression. The other possibility is that there's behavioral and/or environmental aspects that change post-onset that we're not accounting for when looking at onset versus progression. But what about this idea that there's differences between a myope and a non-myope? So pre-onset versus progression. So for some time in the animal model, what we had noticed was in a myopic animal, but not a normal eye, the animal is highly sensitive to pharmacological manipulations. An example of that is atropine, a well-known and powerful drug for the treatment of myopia. If you give atropine to a normal animal, it has no effect on its normal ocular development. But as soon as you start inducing myopia in the animal, suddenly they become highly susceptible to atropine treatment. And so what this has suggested was that the pathways involved in normal and abnormal eye growth, and these are the pathways within the retina, are different in some quite fundamental way. Now, similar evidence is starting to appear in the human literature, with significant differences between myopes and non-myopes. And this is in ERG recordings and corridor responses. And what Schaefel and colleagues have recently postulated is that the myopic retina appears less sensitive to generating growth inhibitory signals. So could this explain the difference between time outdoors affecting onset versus progression? Now, obviously, two questions get driven from this finding. First of all, if the retina does change its state, when does this occur? Does it occur before the onset of myopia? Could it actually be a biomarker for onset occurring? Does it happen at the commencement, or is it after onset? So could it be a driver, or is simply a consequence of myopia development? But a critical question for the field is, what does this mean when we're thinking about clinical treatments? Do we have to treat onset and progression as two different conditions when we think about whether something will work on one or the other or both? But critical to us better understanding the difference between onset and progression and the idea of changes in retinal state in terms of time outdoors is understanding what the potential mechanism is by which time outdoors is actually protecting. There have been a number of points put forward to explain why being outdoors would be protective, from just simply reducing the amount of near work you do, remembering that that's suggested to be a myopogenic stimuli. This seems unlikely now, greater physical activity, and the list goes on. But the four main ones that have been heavily investigated and written about are the idea of differences in the dioptic space, the spatial frequency characteristics of indoors versus outdoors, differences in the spectral composition of the light we experience indoor versus outdoors, especially when you talk about non-visible light, UV, infrared, and so forth. Potential effects on circadian entrainment, and I'll get back to more on this, on the idea of the rhythms we generate by being under what is quite low light indoors versus outdoors. And finally, the idea that just the total luminance, how bright it is indoors versus outdoors, is starkly different. And that's what I'm going to talk about today, because this is what we have the most amount of experimental evidence on, is total luminance levels. But it also could be that all four of these, and most likely all four of these, interact in some way to provide this protective effect associated with time outdoors. So what have we learned from animal models in terms of what bright light does to development in terms of ocular growth? I'm showing here the study by Cohen et al. In which they raised chickens under 3 light intensities, what they referred to as high light, which was 10,000 lux. Now, this is not that bright. This is what you'd experience early morning going outside. Medium light, or 500 lux. This is usually the normal illumination inside a room or a study. And low light, which is only 50 lux, so there's quite dim light. And they followed the development of the chicken eye over 90 days. What you can see is the highlight group finished with this mild hyperopia. The medium light group finished roughly at 0 refractive error, or commonly referred to as emetropia, whereas the low light group developed myopia over the 90 days. Now, what we're starting to understand about the low light is what it appears to do is introduce just a large amount of variability in the refractive development. Even between species, how they respond to low light, some become more hyperopic, some become myopic, but the variability in refractive development increases. And this is most likely driven to what I will go on to later, the effects on circadian and diurnal rhythms, in that once you have too low a light, you can't stimulate this normal cycling within the eye, and this allows variability or noise to enter the system, and therefore myopia or hyperopia or any abnormal refraction to develop. Now, what about bright light and myopia? Again, this is showing the animal model data. And what's been observed is that if you raise an animal under bright light, be it chicken, tree shrew, mice, guinea pigs, or rhesus monkey, so all the species that have been investigated, bright light will prevent the development or reduce the development of experimental myopia. Now, I have a little star next to the rhesus monkeys, simply because we have 2 major models by which we can induce myopia in animal models. I won't go through them, but what we found in the chicken, tree shrew, mice, and guinea pigs is both are equally inhibited by light, but it's unclear for the rhesus monkey whether the second mode of inducing myopia is similarly affected by bright light. So that's still one of the areas that needs further investigation in our field. But in terms of what light does to myopia, I'm just showing you here the data from our chicken work. And this is work I did with Frank Schafel and Arnie Ollendorf back in Germany, as well as Cindy Karuta in my lab in Australia. And what you can see here is as you increase the intensity of light in which the animals are under, the percent protection against the development of myopia increases. And by 40,000 lux, which is still illumination levels you're only going to experience in the early morning, so we can get up in Australia to 150, 160, 170,000 lux. Already by 40,000 lux, you have a reduction in the onset of myopia, or the progression of myopia, sorry, by roughly 90%. So it is a strong effect on the development of experimental myopia. One of the other interesting things is what actually happens in the control eye. So when we're doing these animal studies, one eye we induce myopia within, the other eye is left as an untreated internal control. What you can see here, for example, in the monkeys, here is under normal illumination, so that low room illumination of 500 lux. The black triangles, the black diamonds represent the myopia induced in the treated eye. And you can see in their contralateral eye, it remains roughly hyperopic. If you go to the highlight group, you can see not only does the highlight inhibit the development of experimental myopia in the treated eye, it induces a hyperopic shift in the untreated eye. The same thing is seen here within the tree shrew. You can see here is the untreated eye in the low light group, the untreated eye in the highlight group, and you see the highlight group is more hyperopic. And so this fits if you go back to what Cohen saw, which is the higher the light you experience, you maintain this reserve of hyperopia within the animal. So one of the critical questions is, especially if we're talking about treating humans, is what are the optimal parameters for time outdoors or light exposure based on what we've learned from the animals? And unfortunately, we actually have limited information on the key variables. For example, what is the optimal intensity? What is the duration that is optimal for treatment? Is it a short duration? What is the frequency? Is it multiple periods during the day or one segment of exposure? Timing, morning, afternoon, midday, temporal patterning. There's evidence that brief periods of bright light exposure versus one continuous burst is better. And obviously spectral composition. We know from a number of studies that modulating spectral composition can have a significant effect on ocular growth. Importantly, we don't understand how these variables interact. If I have a greater intensity light, can I go for a shorter duration? If I go in the morning when, let's say it was more protective, do I get to go under lower intensity versus in the afternoon? We don't know how these variables interact. And importantly, we don't know how they interact with other variables of being outdoors: accommodation, pupil size, dioptic space, etc. There's also the problem of confounding factors of differences between species. So for example, we know when we do the monochromatic light, there's been differences reported between species, for example, what blue light does. But even in the bright light, we know that the monkeys don't always show the same response as some of the other species. Animal models are also limited in their ability to assess social, behavioral, and genetic influences associated with bright light or time outdoors. But one of the important things is we need to standardize how we design, measure, and report experiments involving light. And Raymond, who's hosting us here today, has been doing a lot of work in this area. And if we have time at the end, I'd love for him to speak about this standardization, because it's critical when we start trying to compare studies that they are actually comparable in terms of their methodology and how we report light. But from what we've been able to glean from animals so far, what are some of the parameters we can speak about? Well, we know in the animal model that you need a minimum of 2 hours of exposure to see a robust effect. So you can see effects under 2 hours, but to see a robust effect, you need a minimum of 2 hours exposure, with no greater effect seen with 6 hours or greater of exposure to bright light. We know that we start seeing protection at 2000 lux, so that's the minimum light intensity in which we start seeing a difference to control animals. By 20,000 lux, we've reduced the severity by 80%. By 40,000 lux, we've almost abolished onset altogether. We know that it appears to be that light given in the afternoon is better than light given in the morning, although I've put here an asterisk next to it because there is, depending on what paradigm you're using, whether you're talking about bright light's effects on normal ocular growth, myopic growth, how long you give the myopic stimuli, seems to dictate when in the day bright light exposure is most effective. And there is a lot more work that needs to be done in this area. As I noted, there does seem to be some temporal patterning properties. It seems to be that you give light in intermittent bursts. So for example, Lamb did 1 minute on, 1 minute off, or 7 minutes on, 7 minutes off, was more effective in its anti-myopic effects than just one continuous block of the same totality of light exposure. We know that spectral composition, when we talk about monochromatic light, appears to be critical. We know that there's many devices out there in terms of infrared or red light, violet light. We know that just blue or just red channel can really modulate eye growth. But in terms of the composition of white light, not a lot has been done. What little has been done suggests that cool white or blue-centric light appears to produce a stronger effect than red-centric or warm white light. Well, what about evidence in human studies? Well, I'll just read over some of this is by no means a comprehensive list, but some of the data that's been produced. So we know that greater daily light exposure is associated with less axial growth in children over an 18-month period. We know that myopic children exhibit significantly lower amounts of daily light exposure relative to emmetropes. We know that in school-based randomized trials, those protective effects of being outdoors correlate strongly with total duration and intensity of light exposure. It's been shown that a 6-fold increase in classroom illumination was found to reduce the onset, interestingly decrease the progression, and also reduced axial growth over a 12-month period. We know that axial growth and myopia progression are slower in summer than in winter, with a corresponding difference in daily light exposure. But what's really difficult in these studies is to tease out a causal role for light intensity in amongst all the other aspects associated with being outdoors. And this brings me on to what is missing in the field. How do we design experiments in the human clinical setting to look for a causal link of light intensity where we can tease it out from all the other aspects of time outdoors? Like the animal, we really know little about the optimal lighting parameters in terms of intensity, duration, frequency, spectral composition, and so forth. We also know little about what role the other components of being outdoors plays: accommodation, pupil, dioptic space, so forth. And do they have an interaction with light intensity? How do the different parameters of light intensity themselves interact? What would be really interesting for the field is, can we design light-based therapies to not only affect onset, but if we can understand what is going on in progression, can we still use light to affect progression? Could we combine this therapy with other anti-myopia therapies, atropine, orthokeratology, dual focus contact lenses or spectacle lenses, to really enhance the anti-myopic effects within a clinical population? And as I mentioned for animal work, we need to standardize how we measure and report light exposure. And I know a lot of work's been done on this in terms of measuring kids' activities, kids' light exposure, and so forth, in terms of wearable devices. Now, what about the mechanism? What's driving this protective effect of bright light? Well, whenever we think about light exposure and retinal neuromodulation, the first thing that comes to mind is dopamine, which plays a key role in light adaptation, visual acuity, contrast sensitivity, circadian entrainment, and definitely in the animal model, eye growth. Dopamine's synthesis and release is light-driven. You can see here it rises during the day and then falls during the night, showing that nice diurnal rhythmicity. Importantly, we know that the synthesis and release of dopamine is reduced during the development of experimental myopia in animal models. And in all species study, if we pharmacologically stimulate the dopaminergic system, we can inhibit the development of experimental myopia. So therefore, the primary cab off the rank, or the first molecule we looked at in terms of what could be driving light's protection, was that of dopamine. And what we've found is that if you block the release of dopamine by blocking on-pathway activity to the dopaminergic amacrine cells, or if you block dopamine activity at its receptors, you can inhibit the protective effects of bright light. And I'm just showing you some of that data here for the chicken in terms of blocking receptor activity. So here's that figure again, showing that as we increase the light that animals are under, we increase the protection against the development of myopia. But this red line shows us injecting a drug that blocks dopaminergic activity at its receptors immediately prior to bright light exposure. And you can see no longer is light able to inhibit the development of experimental myopia, suggesting that one of the key drivers for light's protection was the dopaminergic system. But what's dopamine doing once it's released? Well, our primary belief is that what dopamine is doing is in ensuring appropriate diurnal cycling and circadian entrainment. I'm just showing you a figure over here on the right. Here's the normal diurnal cycling of dopamine if you expose the animal to normal outdoor light intensity. So you see this nice rise during the day and the fall during the night. This is the rhythm if you keep them under normal indoor lighting levels, so much reduced light intensity. You can see that the rhythmicity is significantly lost. And we think it's that loss of rhythmicity that may bring in variability within the system, noise within the system. But dopamine is also critical in modulating things like spatial, temporal, and color contrast sensitivity. So our ability to see fine detail and colors. It could have a role through that, stimulating dopamine that way. Could be acting purely as a signaling molecule. So it's not to do with its role in the retina in terms of circadian entrainment or temporal and contrast sensitivity, but purely as a signaling molecule. Or it could be a combination of all of the above. What is clear is dopamine is unlikely to drive both. So a lack of dopamine is unlikely to drive the myopic growth, and a stimulation of dopamine is unlikely to directly drive the inhibitory effects. Rather, it will be a part in the signaling pathway to change those changes we observe in the choroid and the sclera. So that thinning of the choroid during myopic growth and that expansion of sclera, it will simply be a point in that pathway. And it's most likely speaking to other molecules, and I've just listed some of them like retinoic acid, nitric oxide, VIP, BMP2. There's evidence around many of these molecules having a critical role in eye growth regulation. So just a summary on this light component. Although further work is required, evidence from animal and human studies would support a role for light intensity in the protective effects of outdoor time. In our animal models, this anti-myopic effect, at least in part, is driven by light-induced increases in dopamine release, driven by that on-pathway feeding to the dopaminergic amacrine cells. What's our working hypothesis, how this all fits in? Well, what we think is happening is the move towards a more indoor lifestyle, a sedentary indoor lifestyle, means that we're not experiencing the same light intensity levels required to sufficiently stimulate dopamine synthesis and release, and therefore we're not creating these normal cyclic growth patterns within the eye. So the message is simple in many ways: get kids outdoors. However, we know that there are a number of barriers, social, environmental, and education hurdles that have been faced in trying to increase the amount of time kids spend outdoors, especially during the school week. This could be simply the weather or temperature. So inclement weather or particularly hot days, it's difficult to send kids outside. It could be pollution, sending kids outside to reduce the potential onset of myopia, but instead increasing the amount of asthma sufferers there are. Light intensity due to seasonal variations. There may be parts of the world where the light intensity is not great enough in parts of the year to stimulate dopamine anyway to protect. And importantly, educational pressures. We know parents really want the best for their kids in educational attainment. And so the idea of continuously swapping out potential classes for time outdoors can sometimes be difficult to sell. So therefore, our group looked at whether we can pharmacologically target the dopaminergic system to mimic the protective effects of being outdoors as a novel treatment avenue, using what we understand about time outdoors. Now, dopamine as a molecule is poor at crossing epithelial barriers, and it is also rapidly broken down within tissue. So it's not a great treatment directly. So you'll see for most neurological disorders involving the dopaminergic system, an example of that is the Parkinson's disease. The primary clinical treatment is the administration of levodopa. And levodopa is the precursor molecule to dopamine. So by administering levodopa, the body will naturally make and release more dopamine. And if we can get levodopa into the eye, the retina will naturally synthesize and release greater amounts of dopamine within this tissue and hopefully inhibit myopic growth. Now, the simplest thing would be to take the tablets already that exist on market and systemically administer levodopa to a child. But what we don't want to do is affect dopamine levels within the brain. These are children with normal neurological structures. We don't want to increase dopamine within the brain. We only want to increase dopamine within the eye. So systemic administration is not appropriate. So therefore, we need to directly target the eye. And in so doing, we'll also be able to reduce the clinical dose. By giving systemically, you must use a much larger dose to account for the losses that will occur through distribution. Now, the most direct way to get the levodopa to within the eye is an intravitreal injection, as shown here, but this is not appropriate for long-term treatment because theoretically levodopa may be needed daily to stimulate dopamine, to keep this cyclic rhythm going in dopamine levels. Therefore, the most practical route, as shown here, would be a topical application, an eye drop. However, anyone who's worked with eye drops knows that it's especially difficult to get the penetration of the eye and to make it to the back of the eye, to the retina, to stimulate the specific changes you are after. But after considerable testing, we have developed a topical formulation of levodopa that is able to penetrate the eye, make it to the retina, and stimulate dopamine synthesis and release. What have we observed here? This is just the preclinical efficacy in our animal model. Our primary animal model is the chicken. And here we're comparing it to atropine, the gold standard for pharmacological treatment and one of the best treatment avenues currently available for human myopia. You can see here the dose-dependent response of atropine in blue, and you can see that it tapers off to roughly about 60% protection against the axial growth that we can induce in the chicken when topically applied. If we don't do anything to levodopa, if we simply apply it in its raw form, you can see we get roughly the same structure as that of atropine, this hyperbolic response. But if we increase levodopa's penetration and stability within the system, you can see here we can actually get this quite significant increase in protection against the development of experimental myopia. And at our highest doses, we were almost able to abolish the development of experimental myopia. And this was a significant increase in effectiveness relative to the gold standard in atropine. The next step is to obviously move on to preclinical safety in animals and really show what levodopa is doing within the system. The first and most important thing we looked at was drug distribution. If you give levodopa to the eye, where is it found? Where does it stimulate dopamine? And we found that topical application of levodopa led to the elevated levels of dopamine in the retina, but did not lead to elevated levels of dopamine within the general circulation. And actually, we could not detect levodopa in the general circulation. This is just showing one such figure from our analyses. This is levels of dopamine in the blood in untreated animals, levels of dopamine within the blood within experimental myopia animals, and levels of dopamine in the blood following levodopa treatment. And you can see there's no significant difference in the amount of dopamine detectable within the blood. Next thing we looked at was ocular surface tolerability and integrity. And we saw no intolerance to the drops in the animals. There was no redness of the eye, no squinting, no retracting their heads. And we saw no effect on corneal epithelial integrity when we assessed this. One of the critical things was what effect did we have on visual functions? Dopamine is a neuromodulator within the retina. Would we change the electrical circuitry within the retina? But we saw no change in electroretinogram outputs within the tissue. We also looked at ocular health, and we found no effect on intraocular pressure, retinal thickness or architecture, and importantly, no signs of cell death or cell stress within the tissue. We also looked at refraction and biometry, and as I said for so many other drugs, although levodopa is able to inhibit myopic growth, it had no effect on normal refraction or axial development in otherwise untreated eyes. So following this, we moved on to a phase 1 safety and tolerability trial. This was a first-in-human, placebo-controlled, double-blind, paired-eye randomized clinical trial held in young adults, males aged 18 to 30, who were treated for a period of 4 weeks or 28 days. These healthy volunteers were randomly allocated to one of two arms, 14 participants in each arm. Arm 1 received a higher dose of levodopa into one eye and saline solution or the placebo solution into the other eye. Arm 2 received a lower dose of levodopa into one eye and a placebo saline solution into the other eye. Which eye received the drug and saline was also randomly allocated within both groups. The participants administered 2 drops to the corneal surface once per day in the morning for 28 days. And we made measures at baseline, 4 weeks of treatment, and after a 4-month washout period. We also had a subset of measures that we undertook at 1, 2, and 3 weeks to ensure safety as the trial continued. Just quickly, you can see a long list of the things we investigated within this population: ocular tolerability, surface integrity, visual function, ocular health, refractive error, and ocular biometry, many of them similar to what we did in the animal model. And the main takeaway point is we observed no significant changes over the trial period. If you wish to know more, I've just given the reference there to the paper with the clinical trial data. So from this, we're now moving on to a phase 2 safety and efficacy trial with colleagues in Singapore. We look to hopefully start enrolling soon and to look at whether levodopa can become another effective treatment in our arsenal of ways of trying to either stop the onset or slow the progression of myopia in kids. And on that, I don't want to go over any further time. I thank you for listening.
Excellent. Thanks a lot, Regan, for a very, very fascinating talk. Very thorough. I think we've learned a lot, but we still have a lot to learn. That's, I guess, the message with regards to light. We have a bunch of questions. I would suggest that we start with the questions coming from the audience. And then along the way, myself and our panelists, Janice and Katharina, will ask you a few questions as well. So let me start with the first question, basically. I think, why are chickens, since you worked a lot with chickens, Regan, why are chickens so loved in the field of myopia and so used in the field of myopia? Why not mice?
So all species have advantages and disadvantages. The chickens, some of their advantages is they're a diurnal animal like us. They're also a social animal like us. One of their biggest advantages is that their eyes, in terms of growth, really do seem to work independent of each other. So what we do treat to one eye has limited effect, although there are cases where people have reported an effect in the contralateral control eye. And having an internal control is a powerful, powerful thing in a biological system, just due to the natural variability you'll see between different animals. They are very fast growing. So you can induce large amounts of myopia in just a week. So I can induce 7 diopters of myopia in a chicken within a week. Where the mouse becomes powerful is when you want to start genetically manipulating the system and looking for what a specific gene or a specific pathway might do within a system. There are less tools available in a chicken compared to a mouse. The disadvantage of the mouse being a nocturnal species and having a lower visual acuity is how much of it relates to the human situation. But all of these species have their place within the field. But as you'll see, historically, the chicken had a large amount of data. I'd say it's actually swinging now. There's a large, I think we'd say a larger amount of data now on, say, guinea pigs and mice. And even monkeys are becoming more prevalent again in terms of research.
Excellent. Thank you, Regan. Okay. Janice, you have a question? Okay. I think we're still having some technical difficulties. We can't hear you, Janice. Let me then move. Katharina, any questions from your side?
Thank you for a great talk. Maybe just one question for me. What is your view on red light therapy and myopia?
So red light therapy is definitely effective. The data is clear on that. What's unclear is still the mechanism by which it does, and therefore us fully assessing the safety of red light therapy. And I know there's been a lot of talk within the field about using laser diodes to induce this change and what it's doing. Is it photobiomodulation? Is it increased blood flow within the choroid and so forth? The fact is, it is an extremely effective technique. What we've got to make sure is that it's a safe technique. And And those studies are underway, I believe, as far as I'm aware, both in both animal and humans. So watch this space.
Excellent. Janice, is the mic working again or not yet? Okay. We'll take it. We'll take it from for this one.
Okay.
So, okay, good. There you go.
Hi, Regan. So nice to meet you, and thank you for the great talk. I just have a few questions about the levodopa studies that you did. I just wanted to ask about, so, you mentioned about 2 drops to the corneal surface. Why 2 drops? Why not the usual 1 drop that everybody uses? Is it because the droplets are of a different volume? How did you arrive on that?
So what we found was that we weren't getting as much of the first. So it comes down to concentration of the drug you can dissolve within solution and how much drug you wish to get to the back of the eye. And when we started with the animal model, the optimal component between dissolvability and transfer to the back of the eye was by providing 2 drops to the eye. Therefore, we moved with 2 drops to the human situation. Now, since then, we've shown in the animal system that potentially 1 drop is more than enough. And this is what we're going to have to look at going forward. But it's a playoff when you're first designing these drugs between the dissolvability and keeping the drug in solution versus how much you want to get to the active site that you want to treat.
I see. Oh, great. Thanks. I have another question about the studies you did on levodopa. Basically, you mentioned that ocular biometrics said that they had no effect on the axial length compared to those normal controls. So how do you correlate that with, its control on myopia?
So that's the thing we're trying to work out, is the fact that when you have a myopic animal, they come susceptible to all types of treatments that aren't there to them when they're in a normal state. So it's as if the pathways are locked. They are, for the most part, intolerant to so many treatments, especially pharmacological treatments. Then you induce some type of optical induced growth. And as soon as you do that, there seems to be a flip in these pathways, and they suddenly become susceptible to all kinds of pharmacological agents. I think that can't even remember off the top of my head, I think we're up to nearly 70 agents that have been shown to be able to modulate growth one way or the other, either increase or decrease, once you seem to unlock these pathways. But very, very few drugs have ever been shown to affect normal ocular growth. And great example of that is atropine. Atropine in an animal model has very little to no effect on normal ocular development. It's pretty much insensitive to you giving it. As soon as you induce abnormal ocular growth, it suddenly has very dramatic effects on eye growth. And we know that atropine transfers into the human scenario where it can inhibit ocular growth. And so this is where we've really got to understand in the human scenario, is there a difference before myopia and after the onset of myopia in terms of susceptibility to treatment regimes, with the new data coming out around the human retina?
I see. So basically, in that new study where you're going to be recruiting myopic children, you would kind of expect that the axial length, there would be some effect on the axial length.
Absolutely. But with all treatments now, what we really got to think about is your treatment aimed potentially at progression, or is your treatment aimed at onset, or can it do both?
Yeah.
And if the mechanisms are different between, in terms of the state of the retina before and after onset, some treatments may be perfectly tuned for preventing onset and have little effect on progression, and vice versa. Or we might find that there's treatments that can carry across both areas. But this is where we really need more information about this idea that the eye is in a different state between pre and post onset.
Yeah, absolutely. Thank you so much. Looking forward to the results of your study.
Thank you.
Awesome. Regan, we have actually 15 questions from the audience, and we have 11 minutes. So we have to have short answers in a way to try to address everybody. So we know that there's a lot of studies on monochromatic light that you mentioned, right? But there's a gap in terms of the spectral composition of white light. One of the questions we have is, what do we know about warm or cool light? You mentioned cool light, but in a way, has indoor lighting ever been trialed for myopia prevention? Example, light treatment, for example, similar to what light treatment for seasonal affective disorders during dark, long winters.
So there are a few studies that have simply increased the intensity of light in which kids are under. And you saw one of the studies I put up showing that there is an effect of just simply increasing the intensity or illumination within the classroom. And it seems to have an effect on onset, interestingly, progression, and general axial growth, be it myopes or emmetropes or hyperopes. Obviously, one of the difficulties is the idea of enhancing the light intensity across all classrooms. It's a huge power consumption, changing huge lighting rigs within the school. So it'll be an interesting one of how far we can go down that path. In terms of the composition of indoor light, we know in the animal, obviously infrared and UV ends of the spectrum aren't present in our indoor lights that we use in the animal. So clearly you can just with bright visible light inhibit myopia. That doesn't mean there's not something in the UV or IR end once you go outside. And it could be an additive, it could be it. We just don't know what component of the spectral composition. What we definitely have not played around with in terms of indoor is truly adjusting warm to cold white light and seeing if there is a difference between the two. Hints from both animal and humans would say that cool white is going to be more effective than warm white, but that's hints. We really have to test it. And what's interesting is this field took off in the early 2000s. We made huge progress, and then we kind of stopped and just moved on to other things, as the field naturally does. New things come up and we start chasing down other rabbit holes. So there is still a lot we don't know about light.
So just to add to this, maybe from our side, with NUS and SERI and NUH, with Janice, we also have a classroom study that's going to be going on, school-based study, testing different spectral composition of light to try and prevent myopia in Singapore. So we'll be talking about this in the future few months.
Very interesting.
Yes.
Very interesting.
So another question, at what age is time outdoors light exposure the most protective against myopia?
Sorry, say that again. You just
at what age? So I guess at what age? I assume it's linked a bit to the onset, right?
So the general idea is that light appears to reduce its strength, it says. It appears to reduce its strength as you get older, but that also seems to be because progression rates are smaller. So it's a question of, is it less effective, or is simply there's less progression, so you see less of an effect with light? But because we're primarily driving after onset, most of the work has actually been done in young kids. Little work has been done in time outdoors in those older populations. So we don't have a strong hold on it. But what little data there is would suggest that there is less effect with age, but there's less progression with age. So it's not clear which one's which.
Got it. And I think we have a bit of a mechanistic question here from Prakash from Australia. Great talk, Regan. Which photoreceptor inputs do modulate the activity of the dopamine system? Is it cones, rods, melanopsin? Could you please share your insight on this?
I would love to know the answer. So what the suggestion was that it was cones to on-bipolar cells to dopaminergic amaretic cells was the assumed mechanism. IPRGCs definitely play some type of role in communicating with the dopaminergic system. Whether it's the light-driven changes in dopamine is unclear. But the mouse data would suggest it's actually rods to A2s to on-bipolar cells to dopaminergic. Now, whether that's a mouse-specific thing or whether that translates to the other, that's what we're looking at right now. Our evidence so far is just showing that it's on bipolar, on pathway. Whether it's rod or cone, unclear. So watch this space. I wish I knew the answer. IPRGCs seem to be less important in the light-induced dopamine release so far in our model. But again, too early to say no role.
Right.
And we know they play plenty of other roles. So.
Okay. Katharina? Yeah.
Yeah. Okay. So, Dr. Regan, just one question from the audience as well. I think everyone wants to know the safety profile of the levodopa eye drops. Do you have any observed or any potential side effects that you see with these levodopa eye drops?
Yeah, so
in your studies?
with levodopa, I mean, obviously early on in terms of human studies, so far we've not seen any adverse side effects. Because we're targeting directly to the eye, where orditudes of magnitude under what levodopa would normally give for, say, Parkinson's. So we're well under where people normally see any adverse effects even kick in within a human population. Problem is, a lot of those adverse effects are seen in a clinical population, so they're a disease state. So what's the drug versus the disease and its interaction? So far, we've seen no observable changes. What's heartening to me is the fact that we don't see a detectable change in levodopa within the blood. So it's not exiting in any great quantities from the eye into the general circulation, and therefore little to no, well, whatever could make it to the brain must be minuscule to date. But early on in all of this. The other thing I always mention is that the great thing about levodopa is the fact that it is a naturally occurring compound within our body. So we're simply trying to bolster your natural system versus quite often we are using a pharmacological agent that's a synthetic as such.
Yeah. Regan, did you check on the sleep patterns of the adults? Was there any change in their sleep patterns after levodopa, with levodopa?
So we had a questionnaire, and with questionnaires, there's only so far they go. There was no reported changes in mood, sleep patterns, and so forth. But because we're targeting more ocular safety, it's an area that will have to be heavily looked at, is in terms of increasing that questionnaire or even some type of diagnostic tool to assess sleep patterns when taking such treatments.
Going back to the question about the mechanisms, right? So linking dopamine release to the spectral composition of light. Two questions from the audience. Do we know which wavelength would stimulate the release of dopamine more?
Not well enough. There's definitely information suggesting certain wavelengths are able to stimulate dopamine release greater. But once we get up to the intensities we're talking about in broad spectrum white light, you're hitting everything. And so the pathway is maximally hit. I think by the 40,000 lux I showed you guys, you're not going to see any greater increase in dopamine release by that stage from the retina. You've kind of maximally hit it. So in terms of specific spectrum, especially when we start entering that first realm of what we call outdoor light intensity levels, would be really interesting. And I know in other fields there is information around the idea of different spectrums having a greater effect on dopaminergic amacrine cells.
Yeah, we have a bunch of questions from the audience specifically about the wavelength, like if you want to modulate the wavelength through contact lenses. So, I mean, I can chip in a little bit here because we still need to do more studies eventually to learn more about the impact of different wavelengths on myopia development and myopia progression. So, I mean, what's your input? Are we ready to start using different color lenses?
Well, I think there's a difference between modulating the inputs or the breakup of wavelengths across a broad spectrum light versus going to monochromatic light. So the great question still in the field is monochromatic light just putting the eye in an abnormal state? It's so used to having multiple color cues. Suddenly you provide it with only one color cue. Is that a different scenario to modulating more red, more blue, more green within a otherwise broad spectrum light? And this is another really interesting area. There's definitely stuff in the animal world. I mean, you can see that the red light, the blue light, violet light, they're all showing, and in animal models, effectiveness in different ways. So there's something in the monochromatic light. How well that transfers to the human situation. I know violet light hasn't been as powerful a response, I believe, in the clinical literature. The red light, depending on what mechanism it's using, is definitely showing very strong effects in the human system. But whether that's red light or some kind of energy-based response, so much still to know.
Yeah. In terms of not increasing the light, but playing on longitudinal chromatic aberration, is that an option? It was asked also by the audience. Do you think that there are two ways light is affecting the eye? One is dimmer, between bracket, normal light conditions, longitudinal chromatic aberration, brighter neurostimulatory effect.
Well, LCA has definitely got an effect in terms of manipulating growth of the eye. It's the question of what magnitude LCA can be used to alter eye growth. And, that's a talk on itself, LCA, and for people much smarter than me in the longitudinal field, chromatic field, talking about just how the eye responds to manipulations in that area. But definitely, I mean, we know that you can alter ocular growth. It's the question of to which you can alter ocular growth compared to, say, just an intensity-based spectral exposure.
Excellent. We'll get two more questions, maybe, Janice.
Hi. So someone asked whether you can administer atropine and levodopa together. I'm not sure whether you've already delved into it in your studies, or is this going to be something in the future?
Yeah, I mean, in animal models, we always mix and match. So obviously in animal models, we've always tried to, the problem with it is atropine is an extremely broad spectrum drug. It can manipulate many, many systems within the eye. And at higher doses, atropine manipulates the dopaminergic system itself. So the question of whether they would have an additive effect, synergistic effect, in the animal models, absolutely, you get a stronger effect, but that's usually because we on purposely reduce the amount of atropine and levodopa we use, so they're not at their maximum effect. You put them in together and you get an additive effect. But levodopa alone, we can get 100% protection. So there's nowhere further to go in the animal model with the addition of atropine. But who knows? A lot more work would need to be done before you start adding atropine and levodopa at the same time to a human eye, simply because they could be striking similar pathways and the eye.
What about light and levodopa, Regan?
If you've got light, you've got enough levodopa.
The combo, don't you think it will?
Light's already done the job for you. You've naturally stimulated the system. So in that sense, levodopa is there because the idea that maybe in the modern world, it is difficult to get this outdoor time, which is, scary. I'd rather hear that we could get kids outdoors, but there are, problems or limitations to trying to achieve that. But it also might be that levodopa could have an additive effect on top of light. So that, if you can only get an extra 40 minutes plus levodopa, maybe that's it, or extra 40 minutes plus atropine. We just don't know. These additive treatments have promise, have a lot of promise.
Got it. Last question, maybe a combo of 4 questions. And then I promise it's already late in Australia. So does the intervention in one eye affect the other eye? And if you want to put your money on another neurotransmitter other than dopamine, what would it be?
You're betting man.
In the chicken, levodopa is given to obviously one eye and doesn't affect the other eye in the chicken in terms of when we look at ERG recordings, if we try to measure the presence of levodopa within the eye or a change in dopamine. So it's not making it to the other eye. Now, I know that there are other studies that have reported pharmacologically treating one eye and finding evidence of the drug in the other eye. Further studies could always look at this. In terms of human, to reduce numbers, obviously we treated one eye and left the other eye as saline. There is no evidence of crosstalk because of the small amount that would make it into the general circulation, but you can never say never, because obviously we can't remove tissue from patient subjects and therefore analyze how much levodopa is in there. What molecule would I put my money on? Oh, geez, there's a long list. I think there's a lot of evidence around nitric oxide. There's a lot of evidence around retinoic acid. And then you get onto a lot of the more genetic markers. And, BMP2 has a lot of evidence around it. In the end, there's a strong probability they're all in the same pathway. They're different steps within a singular pathway. As I said, dopamine is highly unlikely to move from the retina and be the one directly innervating the choroid or sclera in terms of the changes. It's going to be speaking to one of these other markers, most likely. I mean, I can never say never. Dopamine might turn out to do it all, but it is more likely to be in the pathway. So a lot of these retinoic acid, nitric oxide, they actually may all be in the one pathway, just further steps down the line.
Excellent. If no further questions from Janice, Katharina, I think, Regan, thanks a lot for a very, very, very didactic talk. We've learned a lot from you today. We managed to answer all the questions, so thanks for that part specifically as well. So it's been a pleasure having you with us on this webinar. Thanks also to our panelists, Dr. Janice Lam from NUH Ophthalmology and Dr. Katharina Gonadi also from NUH Ophthalmology. And just a quick reminder, we do have upcoming webinar sessions. The next one would be next month on the 9th of July. And it's going to be Professor Padmaja from also University of New South Wales, Australia. So don't miss it. Once more, Dr. Regan Ashby, thanks a lot for this excellent talk tonight. Have a good evening, everyone, and thanks a lot for attending the webinar.